All right, guys, we're back with section 2 of chapter 6, and we're going to talk about substitution. So last section, we talked about solving systems of equations by graphing, and now we're going to solve systems of equations using substitution and solve real-world problems involving systems of equations, and we're going to solve those by using substitution. So that's our vocabulary word, substitution. Well, what's it mean? Well, to solve systems by substitution, you can use a system of equations to find out when the movie earnings are the same. One method of finding an exact solution of a system of equations is called substitution. So here's how we solve by substitution. So when we're talking about movie earnings, suppose you had two different movies that cost different amounts to make and they made different amounts from the theaters. Well, when would their earnings be the same, if at all? Okay, so first step is, when necessary, solve at least one of the equations for one variable. Now, normally you could solve for y, but sometimes you might want to solve for x. Usually, my rule of thumb is if one of the variables already has a coefficient of just 1, solve for that variable because it's already, you wouldn't have to divide. Okay, substitute the resulting expression from step 1 into the other equation to replace the variable. Then solve the equation. So when you do that, you'll get your second equation all in terms of one variable, and then you can just solve for that variable, whether it's x or y. And substitute the value from step 2 into the either equation and solve for the other variable, and then write the solution as an ordered pair. Now, when I read that, your head's probably spinning like, oh my, substitute this into that, then take this and put it here or there. What on earth is he talking about? It's pretty straightforward once we go through an example. So let's use substitution to solve the systems of equations. Notice a system has two or more linear equations together, so you have two equations here. And notice this first one's already solved for y. So step 1 is like done for us. The first equation is already solved for y, so you don't have to do that step. It's already done. Step 2 now is to substitute that in for y in the second equation. You see how the first equation, if you read it, it literally says y equals 2x plus 1. Just like if I said y equals 3, and you would put 3 in for y, or if I said y equals -7, you could put -7 in for y. Well, here, it's just that y equals 2x plus 1 instead of 3 or -7 or whatever. So I'm going to substitute this 2x plus 1 in for y in the other equation. Okay, so the other equation is 3x plus y equals -9. Now, the first equation tells me what y is equal to in terms of x. Y is equal to 2x plus 1, so I'm going to substitute the 2x plus 1 in place of y. All right, now this just has one variable, it's just x, so you combine the like terms since they're on the same side, and then solve for x. Subtract 1 from both sides, then divide by 5, and you get x equals -2. Okay, now I have an actual number for what x is equal to. So step 3 is to substitute that number in either equation to figure out what y is. Okay, now it doesn't matter which one you use, so I personally would use the one that it's easier. Since I know the value of x now, and I'm trying to figure out y, how about we use the first equation again, since it's already solved for y. So first equation is y equals 2x plus 1. Substitute the -2 for x, and you would get -4 plus 1, which is -3. And so your solution is -2, -3, x, y, remember. All right, and if you want to check it, you can check it by graphing both of these, or you can substitute this point into both equations and verify that it actually works. Okay, there's a graph just to see what it looks like, and there's both equations. The blue one is the first one, the red one's the second equation, and they intersect right there. And how would you name this? It would be consistent and independent. Consistent because there's at least one solution, independent because they're separate lines. All right, here's a couple for you to try. Go ahead and pause the video and hit play when you're ready. All right, we're back. So the first one already is solved for y, so I would substitute that into the second one. Now notice the second one is 3 times y, so it'd be 3 times 4x minus 6. Make sure you put it in parentheses so that you know that the 3 is going to multiply all of it, because you're substituting the 4x minus 6 in place of the y, so whatever was being done to the y, like the 3 was multiplying the y, has to multiply whatever y is substituted by. So you'd have 5x plus 12x minus 6 equals negative 1. So you'd have you'd have 17x minus 6 equals negative 1. And then you'd add 6 to both sides. You get 17x equals 5. And then divide both sides by... Did I miss something? Oh, I see what I did. Like, this is really getting weird. Here's what I did. When I distributed the 3, you get 12x. When I distribute the 3 here, I should have got minus 18. Okay? So then you add 18 to both sides. I'm sorry about that. And you would get 17x equals 17. So divide by 17. And you get x equals 1. Now I know x equals 1. I could substitute it back into the first equation. So 4 times 1 minus 6. Vy equals 4 minus 6, which is negative 2. So our ordered pair solution is 1 comma negative 2. All right, cool. All right, so the second system, the second equation is already solved for y, so I'm going to substitute that into the first one and solve for x. So it'd be 2x plus 5 times 3x plus 10 equals negative 1. So it'd be 2x plus 15x plus 50 equals negative 1. So here you'd have 17x plus 50 equals negative 1. Subtract 50. Be careful, that's not negative 49. It's actually negative 51. Divide both sides by the 17. And you get x equals negative 3. Okay, so now that I know x and the second equation is solved for y, I can plug x in for, or plug negative 3 in for x and solve for y. So you have y equals 3 times negative 3 plus 10. You have negative 9 plus 10, which is 1. So the ordered pair is negative 3 comma 1. All right? All right. So if a variable is not isolated in one of the equations in the system, solve an equation for a variable first, then you can use substitution to solve the system. So the first equation has a coefficient of 1 in front of the x. So like I said earlier, if one of the variables has a coefficient of x, solve it for that one. So you would take that equation, subtract 2y from both sides, and get it in terms x in terms of y. In other words, it's solved for x. X equals 6 minus 2y. Then step 2, I'm going to substitute the 6 minus 2y in for x in the other equation. So the other equation, 3x minus 4y equals 28. I'm going to plug the 6 minus 2y in for the x there. So it's 3 times 6 minus 2y minus 4y equals 28. Notice I put the parentheses in here because the 3 has to distribute to everything you substitute in for the x. So when I do that, I get 18 minus 6y minus 4y equals 28, which is 18 minus 10y equals 28. Then I got to solve for y. So subtract 18 from both sides. So these 18s would cancel here. And you would have negative 10y equals 10. So divide both sides by negative 10, and you get y equals 1. So now I know the value of y. I got to figure out x. Well, the first equation has a coefficient of 1. It's not solved for x. I mean, I know we solved for x down here, but you want to always use the original equations once you're plugging a number in. Okay, the first equation, it's going to, if I'm substituting the value of y, the first equation is going to be a little bit easier to get x by itself. Okay, so plug in negative 1 for y. You get x minus 2 equals 6, and then x equals 8. And so the solution is 8 comma 1. All right? Okay. So here's a couple for you to try. Go ahead and pause the video. Okay, we're back. All right. So the first equation, or the first system rather, the second equation has a coefficient of 1 in front of the y. So I would add 3x to both sides for that one and get y equals 3x minus 13. And then I'm going to plug that in for y in the first equation. So 4x plus 5 times 3x minus 13 equals 11. So 4x plus, you have 15x minus 65 equals 11. So you'd have 19x minus 65 equals 11. And add 65 to both sides. We have 19x equals 78. And let me double check my work here. I'm getting mixed up. So what happened here? Distribute, got that. 4x and 15x. Oh, it's not 78. It's 76. Why didn't you tell me that? There we go. And then divide both sides by 19. And you get x equals 4. Once I know x equals 4, I can substitute it back into the second equation. So y minus 3 times 4 equals negative 13. So y minus 12 equals negative 13. So add 12, 12, and then you get y equals negative 1. So your ordered pair is 4 comma negative 1. Alrighty? All right, cool. Now, if you want to know the answer to the second one, just shoot me a message and say, Mr. Antonucci, I need to know the solution or the worked out solution for 6.2 guided practice 2B. I will tell you that the answer is 3 comma 4. Okay, so if that's the answer you got, more power to you. All right, so we're going to talk about what happens when you have no solution or infinitely many solutions. So let's use substitution to solve this system of equations. So substitute 2x minus 4 for y in the second equation because this first equation is already solved for y. So I'm going to plug 2x minus 4y in for y here, distribute the 3, and the 6x's cancel, and I have negative 12 equals negative 12. Well, when you have negative 12 equals negative 12 and the variables all canceled, you have a true statement. And remember, when you have a true statement, that means there's an infinite number of solutions. So this system of equations would be consistent and dependent. Okay? All right, let's try these ones. Go ahead and pause the video. All right, we're back. So for the first one, I'm going to substitute 2x minus 3 in for y. So it'd be 2x minus 2x minus 3 equals 8. And I'm glad this happened because notice it's 2x minus y. So you still have to put what you substitute in for y in parentheses, but now you're going to distribute the negative. So it's 2x minus 2x plus 3 equals 8. Because the minus distributes here, makes it a minus 2x. It distributes here, and you have minus and negative or a positive. All right, the 2x's cancel, and I have 3 equals 8, which means there's no solution. So that system would be what's called independent, or inconsistent rather. There's no solution. Okay. All right, 3b. So here's what we're going to do. We're going to pick one of the equations. Neither one of them is already solved for x or y, and neither one of them has a coefficient of just x or just y. So what I'm going to do is just pick one and solve for either x or y. So I would pick either solve this one for x since the 4 is positive, or solve this one for y since the y is positive. So I'm going to do the first one. So if I solve that for x, I would have 4x equals 3y plus 1, then because you added 3y to both sides, then divide both sides by 4. Okay, you have x equals 3/4 y plus 1/4. Then you're going to substitute that in for x in the second equation. So you have 6y minus 8 times what x is, 3/4 y plus 1/4 equals -2. So you have 6y. Now you're going to distribute a -8. -8 times 3/4. Let's see that up here. You put the 8 over 1, you can cross-reduce the 8 and the 4 to -2 and a 1. So you'd really have -6 over 1, which is just -6. So it'd be minus 6y. And then the -8 times a fourth. Well, think about it. What's a quarter of 8? 2. So a quarter of -8 would be -2. So the 6y's cancel, and you have -2 equals -2. And that's the same number, true statement, variables canceled out. So I have an infinite number of solutions, so my answer would be infinite number of solutions, and you would call it consistent and dependent. Alrighty? Alright guys, that's it for this video. Please stay tuned, and we'll start the next one in just a minute.